Opposites attract. It's a well-used phrase, but in the world of electric charge, it's completely true. But we need to understand it better than that if we're going to work with capacitors and touchscreen devices and computers and the like. What we really want to try to understand is the connection between charge and potential and electric field strength. We're going to look at equations so that we can predict and design products, but we're also going to look at it visually, understanding what the fields look like and how those can be used to help us in those designs. Let's start off with charge. What is it? Think for a moment. Can you come up with a definition of charge? Well, I hope you thought about it, but you may well have struggled because although I'm sure you know what charge is, it's a difficult thing to really define, and that's because it's so fundamental to physics. Things have got charge or they haven't. Just like how things are magnetic or they're not. Things have mass or they don't. Quarks have strangeness or they don't. So charge is a fundamental property, and what we can say is that if an object has charge, it will experience a force in an electric field, or more correctly, in an electromagnetic field. Here is a charged particle. It's a sphere because A, that is often the case, and B, it makes life a lot simpler. I've drawn a big circle, but we're going to treat everything as a point charge. What that means is that although the particle looks this big, mathematically we're going to treat it like a tiny, tiny dot. We can do this because the maths works out the same either way in the end, but the equations for the sphere look like this. Now feel free to dig into Maxwell's equations if you like a challenge. But let's get back to what we need to know. This point charge has electric field lines coming from it, much like you would have drawn magnetic field lines coming from a north pole. The field lines leave the surface at 90 degrees. They are evenly spread out. And they go away from positive and towards negative. And here's a drawing for a negatively charged particle. And for completion, here's one for a neutral particle. And here are a few for some other shapes. You can see how the patterns obey the same kinds of rules. Anyway, back to the positive point charge with its field. The field is strongest near the point charge. We can see that because the field lines are closest together here. So the point charge will exert a force on other charged particles depending on the size of its own charge and the distance between them. But how much? Charles Coulomb, a French physicist, was the first to describe this, and Coulomb's law states that any 2 point charges exert an electrical force on each other that is proportional to the product of their charges and inversely proportional to the square of the distance between them. Right, grab your pen or whatever you're using. I'll repeat that, and you should try and write it down as a formula. Any 2 point charges exert an electrical force on each other that is proportional to the product of their charges and inversely proportional to the square of the distance between them. Force is proportional to the product of the charges, so F is proportional to Q times Q. Big Q times small q. I'm going to write here. And force is inversely proportional to the square of the distance, so F is proportional to 1 over r squared. Putting it together, F is proportional to QQ over r squared, or F equals KQQ over r squared, where that constant of proportionality K is actually equal to 1 over 4 pi epsilon 0. Okay, 1 over 4 pi epsilon 0. Epsilon 0 is the permittivity of free space, the measure of how easily an electric field can pass through a vacuum. It's constant and has a value of 8.85 times 10 to the minus 12 farad per meter. It's about the same for air, and we're not going to worry about anything else. So now we have an equation for the force between two electric charges. We should try it out. In the next lesson video, we're going to look at an example question where we're using this calculation, and then we're going to dig more into electric fields.